Okay, everyone, we will start, please. This presentation will be done remotely by Jeff Bailey. And so the sound is not very good, so I please ask you to be quiet. Okay?
Okay.
Yeah, and Jeff, speak slow. Okay?
Speak what?
Slow.
Slow, okay. This is the presentation.
Yeah,
okay,
you can start.
I want to acknowledge my authors and give a special congratulations to the São Paulo LMA team for receiving a NASA Group Achievement Award. We installed 12 sensors in about a month, which I think is completely remarkable. Okay, outline. Main goal, make sure users understand the complexity and careful usage of the São Paulo LMA data set. I'll go over the network geometries a little bit. And we had a significant TV channel 9 noise source that we need to address. Then I'll go over the noise filtering and elimination. And we'll look at a little bit of data analysis, statistics, and the conclusions. Okay, before we get into the noise analysis, I wanted to show you an example from 0119, January 19th at 2300. This is with the noise removed. And when carefully analyzed, the LMA provides excellent performance on par with any LMA network. Okay, upper right is the network geometry. One thing I want to say there is the blue line here is the 3D area of the LMA. Down below is the time of arrival technique, and it's a GPS sensor at each site. Okay, now we're looking at the noise characterization. We have a primary noise source, which is located at a TV channel 9 tower, N1 here. Other noise sources exist, but contribute a small fraction compared to the primary. N2 is the next largest. Main noise source curves with altitude. There's a hyperbola here. Projection is down here on the plane, which is this guy here. The TV sync pulses create 60 hertz multiples in the timing difference plots, which are here. And what we actually ended up using was a vertically oriented cylinder of varying radius that can effectively filter the noise. And I want to point out that in this plot over here, 95.8% of the total data there is located in the green on that plot there, which is a half kilometer. And the histogram inset peaks at about a half kilometer, another peak at 1 kilometer, and mostly gone by 4 kilometers. Also, we need to say that the real lighting tends to dominate the noise, and the noise tends to be a lower signal strength. Okay, this is noise filtering criteria and justification. I plot the noise filtering versus distance from noise site here and here. On the left is an all noise period at half a kilometer here. Notice the scale is 96 there. On the right is a good active lightning period. Again, 0.5 here. Notice the scale is 1 to 5 there. Some days need larger cylinder radius from approximately half a kilometer to maximum 2.5 kilometers. The histogram of number of sources per flash drops quickly on the right, and here's 5 sources here. So we take out the singletons, or we require 5 or more sources per flash to take out the singletons on the right. We'll also be submitting a new data set, and we'll have the noise taken out and the singletons we've flagged in the process data. Okay, here's our example noise rejection and lightning period from February 27th, 0300. Prior to filtering, these are XLMA type plots, and you can read the labels, I think, on those. Prior to filtering, histogram was dominated by noise at low altitude here. After we eliminate the noise before grouping into flashes by applying a 1 kilometer cylinder case, a N1 in this case. 1 kilometer cylinder remove 52% of the noise, and the singletons removed another 7.7% of the noise. Singletons are all the scatter here. And afterwards, the lightning histogram dominates the noise. Filtering effectively eliminated most of the noise while retaining most of the lightning, including low altitude sources that likely indicate real cloud to ground flashes, basically here. Okay, now after we remove the noise, we've got to show you a little bit in terms of a timing and spatial comparison. Upper left is São Paulo LMA in green, Liz events in gray, Lynette in red, and Lynette in black star, and Earth Network's red star. Upper right is the same thing, except now I've done just the TD sensors. Lower left, this is the actual time from 80 to 200 seconds after 1900 of the Liz overpass for that long box. Here we've got Liz flashes, groups, and events, MNDAT, ADDNet, StarNet, TLS VHF, TLS LF, which there was no data on that day, and then we'll show good timing alignment there. Note that Liz has two FIFO overflows here of approximately 20 seconds each, and on the right is the trim burrs visible with Liz flashes overlaid and the magenta stars. The data is good data set for any comparisons with all sensors. It has good temporal and spatial correlation. Some Liz events are not detected here, which turns out to be this star down here, but that looks like that's a lower luminosity cloud, which may not be electrified. The majority of the flashes are detected by most systems, but with different levels of detail. Earth Network appears to have a bias towards higher altitude. That's here, which is on stands to do left. And the next slide, I'll show you an animation of this one here for the Liz overpass. Okay. What I want to point out first is red lines up here. That's the current second that's being displayed. Okay. At first, there's no lightning in the Liz field of view. Then it goes into the FIFO overflow, and you don't get any Liz data until right there. So the first 50 seconds or so, you don't get any data in the overpass. Okay, so now it's going through. There are some ones that it misses in here that everybody misses. Note that this is coming up a little bit here, and we're about getting close to coming into the second FIFO overflow, which there would be no lightning again. Other comments. Nobody detects all events, including São Paulo LMA. São Paulo LMA and TLS 200 VHF, not shown here, are about tied for detecting Liz events. Liz does not detect all flashes. If I put the singletons back in for the LMA data, then it does correlate more with some of the Liz events that were missed. Okay, here's the statistics for 1 hour on February 10th, 2012. And basically, bulk statistics provide a sanity check of the data. Otherwise, you need to check the data closely. E.g., it should look like this. If it doesn't, then you need to look real closely. Any residual noise appears not to significantly affect the statistics. And some key results here. The min flash rate here is proportional to the number of sources, but not the max flash rate. Flash duration is not a function of distance from network center here. You get more sources, also in, which was expected. And the mean charge centers for this one are about 5.5 and 11 kilometers. I also wanted to point out the colors over here. Min is red, mean is in black, and max is in green for the ones that matter here. This is an example of the data quality for, again, February 10th. This flash has 2341 sources, has a duration of 1.23 seconds. Large extent, approximately 35 by 35 kilometers. Excellent detail of charge and channel structure. This is a 3D version of that over here. Lynette is black stars, which you can see a few there. And Earth Network is red X, which you can see a few here. Most of those had around 10 to 20 sources for this flash. Okay, now we're on to our conclusion slide. Data was collected from November to April. When carefully analyzed, this LMA provides excellent performance. And I wanted to point out on some of the previous presentations, if you have not removed the noise, then you could have biased at least the bulk statistics type things. Let's see okay. So this can source reverse effect on the light data. Lightning data tends to dominate the noise. Noise must be removed to generate meaningful monthly climatologies during Chuber, which is not shown here, although Rachel showed one earlier. Good correlation was found between lightning detection systems. All the data sets will be real valuable for doing the GOES proxy activities. When you compare to Liz, you need to be careful with it and make sure you got the right timing and spatial correlation. And we did not find any significant Liz offsets. We will be doing a detailed flash analysis, bulk statistics, and climatologies. And as I mentioned earlier, we did a RISE data set with the primary noise removed, but we'll leave the signal to them because some of them can be real, but we'll tag those so that you can actually take them out easily. And I just wanted to leave you with the other 36 total flashes in that 1 hour period on February 10th that were greater than 1,000 events. Questions?
Thank you, Jeff. So I'll get any questions. Earl?
Hi, Jeff. It's Earl. First of all, many thanks for your help with us, with looking at the LMA data and the question about how many sources per flash in the vicinity of the Val de Paraiba radar. You did have a plot of number of the occurrence probability of the number of sources per flash earlier in the talk. Can you pull that up?
Give me a second here. Back here. Talking about that one?
Not that one, I think.
It was the one where it was dealing with the noise sources. So it's the cumulative distributions of the noise.
That's it. It was a big plot on the right-hand side of the slide.
That one?
No.
Near the beginning.
Here, let me step through and you tell me which.
This one, yeah, the right-hand plot right there. Too far. One back. Okay, page 7, yeah.
So what's the question?
The question is, does that on page 7, the right-hand little subplot?
Page 7, okay. All right,
That's
page
it,
7.
exactly. Okay, now you only show that to 100 sources per flash. Does that plot pertain to the center of the network? Where does that plot pertain? And do you have a plot like that for the vicinity of the X-pole radar, for lightning in the vicinity of the X-pole radar?
Well, that's for that whole 1 hour. Now I did cut the limits off on it a little bit to be able to show the single times go up to like 40,000 on the left-hand axis there. You also notice I have the cumulative on the right side in red, and at half a kilometer, we're up at almost 90% of all the data.
Okay, but to do certain kinds of analysis, you need many more than 100 points per flash, and so I'd like to know what that.
Well, we haven't. I mean, like I said before, we have those 36 during that hour that have more than 1,000 sources per flash. So the axis here goes way out.
Okay.
I cut it off so I could see stuff better on this one.
Jeff has
Uh,
a storm day clock as an example of him that you would want him to do it. Okay. Jeff, this is Ken. So go to your backup slides that show the storm day plots. Yeah, the matrix of storm
That
day.
one?
No, the matrix that kind of gives a summary of the months of the data. There you go.
Oh, that one, okay.
Yeah, I think what Earl would want would be something like that, only indicating the number of flashes with more than 100 sources or more than X sources. I'll give the mic back to Earl now.
I have to tell you that this plot is a little bit preliminary. It's for December of 2011. All the stuff is on the left side, which is basically with the noise, and then on the right side it was without. But there are a few days that are actually missing in it that have some lightning on that.
Okay. Well, we can
We can talk later, Earl,
we can
if we
talk
need
it
to
offline.
on that.
Yeah.
Any more questions?
You're welcome.
So I think it's Ken, right?